Hello everyone, myself Chaitanya Kumar and I am going to take the tute on basic electrical circuits. So these are preliminary questions and we will start with the first question. So the question says that we have a waveform x of t and we need to find the dx by dt, that is the differentiation of this waveform at t is equal to 2.5 seconds. And other thing that we need to find is the complete, also need to sketch the complete waveform between time 0 to 5 seconds. Now, let us see how we proceed with this example. So, this waveform consists of multiple segments of straight lines. Now, let's consider the first segment, that is from 0 minus to 0 plus. In this, there is a step in the waveform x, and its differentiation will be an impulse function multiplied by the size of the step, that is 5 dx, 5 del of t. Now, from 0 to 1, the waveform that we have is a flat waveform, hence its differentiation will be 0. Now, from 1 to 3, the waveform is a waveform with a straight line with a constant slope of minus 5, and hence our differentiation will be equal to the slope of this straight line, that is minus 5. And from 3 to 4, again our waveform is flat, hence our differentiation will be 0. And from 4 minus to 4 plus, our waveform is again a step from minus 5 to 0. Hence, our dx by dt will be an impulse that is multiplied by the step size, that is minus 5. And here we will have, since this step occurs at t equal to 4, so the time argument will be t minus 4. Now, this is the waveform for dx by dt. So at t equal to 0, we have a step, we have an impulse with multiplied by the step size, that is 5. Then for 0 to 1, we have 0. Then for 1 to 3, we have uh, dx by dt, that is of minus 5. Then again 0 from 3 to 4. And at 4, again we have a step, and then it remains 0. So this is how we proceed with this question. Now it's the same waveform in the second question, but this time we need to find the integration of this particular waveform. We need to find its value at t equal to 3.5, that is over here, and then we also need to sketch the complete waveform. Now let's proceed by looking proceed step by step with this problem. So from 0 to 1, we have the waveform that we require is integration from 0 to t x of t dt. So since this x of t is a flat waveform from 0 to 1, so its integration will be just the flat waveform multiplied by time t. So it will look something as depicted in this image. So we will have a straight line with a slope of 5. Now from 1 to 3, we have a straight line that is of the form mt plus c, where t is the time argument. Now to find the m, that is the slope, we calculate the slope from here to here by having the difference between the y-axis and divided by the difference between the x-axis, and that comes out to be minus 5. And to find the constant, we put in the slope minus 5 in this equation, and at t equal to 1, the value of this x of t is 5. Hence we plug the value of the x and the time in the above mentioned equation, and find the coefficient, the constant, and that comes out to be 10. Now we know that from time period t equal to 1 to 3, our x of t is, so we have x of t as minus 5 t plus 10. And when we integrate it, we will integrate it in two parts. First integration will be from time equal to 0 to 1, and the second integration will be from time equal to 1 to time equal to t. So previously we saw that time equal to 0 to 1, our waveform looked like this. So we had at 1, we had the value 5. So from there, the total integration from time equal to 0 to 1 comes out to be 5. And this integration will be over the waveform present over here. And that comes out to be this expression, that is minus 5t square by 2 plus 10t minus 7.5. On simplifying it, we get a parabolic equation that looks like this. So now this equation, if you uh, see, its value at t equal to 1 comes out to be 5, and at t equal to 3, it also comes out to be 5. And in between 1 and 3, this is since this is an inverted parabola, as the coefficient of t square is negative, so it will do something like this, and at 3 it will come back again to 5. Now, one thing that we can see in this curve is, uh, as we look at the as we look at the waveform of x. Now, the waveform of integration of x. For the waveform of integration of x, this is just the derivative. Now, since the derivative is 0 at point t equal to 2, so that thing we can exactly see in our equation. So for t at up to t equal to 5, it goes as a straight line. Then it is an inverted parabola. Now you can see that at t equal to 2, we have a derivative of 0. That is due to that, our waveform of integral of x is a flat at t equal to 2. So this is an intuition that one can develop from this question. And for the last segment, that is from time equal to 3 to time equal to 4. Again, the integration we will do in two parts. The first part will be 0 to 3. Now we know, since at t equal to 0, the integral waveform is at 5. So this part will become 5. And the next part, since it's a flat waveform, since the x of t is flat in this segment, so again it will be minus 5. Again, it will just be a flat waveform multiplied by the time. And on simplifying this complete expression, we get this expression for integral of x of t from t equal to 0 to t equal to 4. And it basically, since it's a negative slope, it goes down. At t equal to 4, it comes to 0. Now from t equal to 4 onwards, since the derivative is 0, as we can see, after that x of t is 0, so integral of x of t will not change from the value at t equal to 4. And since the value at t equal to 4 is 0, it will just remain 0 for the rest of the time. Now, at the asked time t equal to 3.5, our value comes out to be 2.5. That can be easily calculated by this. Now the third question is, the figure shows x of t, and we are asked that which of the choices best represent integral 0 to t x of tau deta. Uh, so, uh, we can see that this is a cos waveform, and through basic trigonometry, we know that the integral of cos of t comes out to be sine of t. So this is an analytical way to solve it. Now, since the options are given to us, so let's see what is wrong with each of the options. Okay. So now the first thing, that any waveform that is the integral of some particular waveform cannot have a step in it So this kind of discontinuities are not possible in an integral waveform unless and until in the actual waveform we have impulse functions. Now, since in this waveform we don't have any impulse function, so its integral waveform cannot have any step. So B option is eliminated with this logic. Now let's move on to other options. So we know that the waveform should start from zero. In the other option, since x of t is the derivative of the waveform, the integral waveform, and in the first segment the derivative is positive, so the integral waveform must increase. Now let's see, out of A, C, and D, only A and C are increasing in the starting. D is decreasing. So D cannot be the right answer. Now, the next thing, the third thing that we can see over here is at this particular time instant, that is the let's say the time period of this waveform is t. At t by 4, it's the derivative of the integral waveform, that is x of t, becomes 0. So in this, due to this, what we must see in the integral waveform, that the integral waveform must become flat for that instant. Now let's see which waveform out of A and D is flat at this instant. So this is at t by 4 for this, and at t by 4 of in C option we have this. So we see that for C this waveform is continuously increasing, which is not possible with derivative 0. So A is the correct answer. And since we discussed earlier, since integral of cos is sine, so from there also we get sine, and this is a sine waveform with respect to the time axis. Now we have two questions over here. This is a decaying exponential kind of waveform, x of t, and we are asked to find the dx by dt and the integral wave. Now, dx by dt, looking at the curve, we see that, so first of all, there will be an impulse. So, impulse is there at the origin in each of the cases. So, and why we will have the impulse? We will have the impulse because there is a step in the original waveform. Now, after that, what we need to observe is the original waveform is decreasing. Now, since the original waveform is decreasing, its derivative must be negative. So, B and A and B cannot be the correct answer. Okay. Now, at a very large time, that is when t tends to infinity, we see that the uh, output becomes flat after some time. That is, there is no longer any increase in the x of increase or decrease in x of t. This suggests that as t tends to infinity, the derivative of dx by dt must go to 0 so that the waveform can become flat. Now, out of C and D, only in C option, we observe that the waveform goes to 0, hence C is the correct answer. Now, analytically, this expression, this is basically, this looks closely as a decaying exponential, that is e to the power minus t u of t. So, if we differentiate it, we get uh, del of t plus sorry, yeah, plus minus t minus e to the power minus t u of t. This I have differentiated using chain rule. First of all, the differentiation of u of t is del of t, and that when multiplied by e to the power minus of 0, so this term is a unity, so this will just remain as it is. And the second in the second one, the second function is as it is, and the derivative of the first function, that is e of minus t, that comes out to be minus of e of minus t. So from here also we can see that C is the correct option. Now let's move on to the integral of this particular graph. So in integral, as we saw before, that integral cannot have a step unless and until there is an impulse at the origin. Now, since there is no impulse at the origin, so option A and option C are eliminated. Now, out of option B and D, let's so the derivative is a positive. The derivative is positive. That is, the waveform x of t is positive. Hence, the integral waveform should increase. Now, only in case of B, we see an increase in the integral waveform. Hence, B is the correct answer. So, these were the questions that I had. Thank you.